at 150 miles per hour. A human body hitting a solid surface headfirst doesn't survive, not at 60, not at 80, certainly not at 150. The force involved isn't just lethal, it's architectural. It collapses structure. It snaps vertebrae like dry wood. Now double that speed. Triple it. And aim it directly at a target. Same physics. Same force equations. Same gravitational acceleration. Same collision. And it walks away. That question has a real answer. And the answer is nothing like what you'd expect. Because stronger bones aren't it. Thicker muscles aren't it. A more robust skeleton, isn't it? The true answer involves a collision that, by the time it actually happens, has already been solved. Before we talk about impact, we need to talk about something that happens minutes earlier. Because the survival of the eagle's neck doesn't begin at collision. It begins. Age its eyes. What that means in practice is this: from 300 meters in the air, an eagle can resolve the individual muscle movement of a rabbit's hindquarters. It isn't seeing a rabbit. It is seeing the rabbit's intention to move. The visual speed advantage alone would be remarkable enough. But there's something more important happening inside the eagle's neurological system. The eagle's vestibulo-ocular reflex, the mechanism that keeps the eyes stabilized while the head moves, operates with a latency so low that the image of the prey remains essentially motionless in the bird's perception, even while its entire body is rotating at high speed through a 45-degree stoop. Its world is locked, frozen, stabilized. And here's the critical insight. This is predictive targeting. The eagle builds a three-dimensional model of the prey's probable movement arc, counting for speed, terrain, likely escape direction, and locks its trajectory not onto the current position, but onto a predicted intercept point. It is solving a physics problem at 150 miles per hour. But here's what nobody tells you about that. Here is the first thing that surprises people who study this. Eagle's neck is not stronger than yours. It is, structurally speaking, not designed to absorb the impact at all. So if the neck isn't the absorber, what is? The answer requires you to rethink what you think the eagle is doing during a dive. The body begins a sequence that engineers call anticipatory load preparation. The muscles don't wait for impact to respond. They preload against it. But muscle preloading is only part of it. The wings, which you might assume are simply tucked during the dive, are doing something far more precise. In the final seconds of the dive, the eagle flares its wings, subtly at first, then dramatically, using its own body as an aerodynamic brake. Think about what that means for the collision physics. The eagle entered the stoop at perhaps 150 miles per hour. At contact, the actual speed may be 80.70. In some species, closer to 50. The fastest part of the dive is in the middle, not at the end. There is a moment in every dive, and this is not a metaphor, where the eagle loses the option to abort. It is a neurological event, a threshold crossing. Motor commitment, the point at which a planned movement becomes irreversible, occurs in the eagle's motor cortex roughly 1.5 to 2 seconds before impact. After that point, the muscular sequence is executing on locked-in neurological instructions. The conscious system, such as it is, has handed control to the body's automated programming. But in the eagle, this handoff is more total, more final. Because what happens in those final 1.5 seconds isn't instinct in any simple sense. It is a coordinated, sequenced biological program with a specific order of operations that executes autonomously at a speed conscious thought cannot match. The eagle cannot second-guess the approach. It cannot flinch at the last moment and redirect to a safer angle. The sequence is running. The body is executing. Which means, by this point, the question of whether the neck survives was already answered seconds ago. In the air, before any contact was made. But how? Team Nina 600 milliseconds. The wings begin their maximum flare. Surface area doubles in less than a third of a second. Speed is dropping hard. The aerodynamic system is dissipating kinetic energy into the air column, behind the bird. Teamness 400 milliseconds. The legs extend. The talons spread. This is not preparation for grip, not yet. This is physical geometry. By extending the legs, the eagle increases the distance between the point of first contact and the cervical spine. The longer that chain, the more time and distance the impact force has to distribute before it reaches the neck. This is engineering. Passive force management through skeletal geometry. Teamness 200 milliseconds. The deep cervical muscles, the network of small, powerful stabilizers surrounding each individual vertebra, reach maximum preload tension. This is the body acting as its own crash harness. A suspension bridge under tension is dramatically more rigid than a slack cable. The eagle's pretension cervical system has, in effect, become a different structure than it was 2 seconds ago. Contact. In the milliseconds that follow, the legs flex at the knee and ankle. Absorbing the impact like landing gear on a carrier aircraft. The musculotendinous units in the lower limb are acting as biological springs, compressing, storing energy briefly, then releasing it, not as a shock wave upward into the spine, but as rotational momentum redirected outward through the wings. T plus 80 milliseconds. The wings are now performing active roll correction. The body's angular momentum from the dive, which, without intervention, would continue rotating the head downward into the ground, is being managed by real-time wing adjustment. This is not passive. This is not mechanical reflex. This is active proprioceptive feedback. The body sensing its own rotational state and issuing corrections faster than any conscious process could. And through all of this, the deceleration, the contact, the force absorption, the rotational correction. The head doesn't move. Because the 14 vertebra cervical chain, preloaded, geometrically aligned, supported by a deep muscular network at peak tension, is now a stabilized strut, not a flexible neck. The head is locked to the body's center of mass. The collision happens below it. Around it, through it, but not to it.
What you just watched was not a lucky animal surviving something it shouldn't. What you just watched was the output of approximately 60 million years of iterative engineering. Every system we described, the foveal targeting, the neural latency, the anticipatory preloading, the aerodynamic braking, the geometric force distribution, the tendon elasticity, the proprioceptive correction. None of them evolved for this moment. Each one evolved for a different problem, a different pressure, a different survival challenge. At some point in evolutionary time, millions of failure iterations we will never see, they converged. They integrated. They became, together, a unified collision management architecture. We built crash test laboratories to understand impact physics. We developed crumple zones and airbags and 5-point harnesses. We invented materials science to engineer structural protection into vehicles. Engineer structural protection into vehicles. And then we look at this bird and realize it solved a harder version of the same problem. At higher speed, with higher precision, with a living biological system, subject to injury and fatigue, and developmental constraints. In a time frame that dwarfs the entirety of human technological history. It is not a bird with strong bones. It is not a hunter with fast reflexes.